Are we live? I guess we are. What language are we in?
So that offers a few things that...
English. Yeah, hyper. I feel like doing a chilled episode today. Welcome to Lasergurkenland, reachable under lgl.sillyhoon.com, and today we're going to watch a talk by I don't know whom, but it has the title 35C3 Safe and Secure Drivers in High-Level Languages. It's uploaded on the mediaccc.de channel. It was uploaded in 2018 and has currently 5,000 views. So if you're interested in that video, check out the original. I have a link to that in the description. Other than that, go join this Minecraft server, and yeah, I should probably get some TNT. Yeah, let's go. Oh wait, I should probably check, are we live? Yes, we are. Cool.
Driver development has been dominated by C for many, many years, and it sadly still is. C is inherently flawed, and there are better alternatives, but those are always fighting against the stigma of being slow and cumbersome to use. So, today here our speakers are going to tell you that this is in fact not true.
Where am I coming from?
High-level drivers with high-level languages, and they perform very well. Here to talk about this are Paul, Simon, and Sebastian. Warm round of applause, please.
I'm still not very used to the look of these new tools. I don't know, they look like wooden tools to me. They don't look very valuable, but this will probably come with time, I guess.
Thank you. Yeah, I'm Paul, with me are Simon and Sebastian. Just a few quick notes before we get started. I speak quite fast usually, so sorry to the translators and sorry to everyone listening. If you are watching this on a stream recording on media.ccc.de, there is a button to your right where you can reduce the playback speed. If you are watching on YouTube, you can also reduce the playback speed somewhere. Also, please.
Should we do that? I don't know, I never do that. I usually just increase the playback speed, but as I said, I really want a chilled stream today, so maybe let's actually do that. That's so funny. Playback speed, let's go 7.75.
Like and subscribe on YouTube.
Ooh, it sounds so robotic.
You might have already seen that they have quite a lot of names up on these slides today.
No, the audio quality is not getting any better. Let's continue with normal speed.
And these are all the people who somehow contributed to this talk, and these are all my students. With me today are Simon and Sebastian, who both did a bachelor thesis with me. I'm a PhD student at Technical University of Munich, and I'm researching performance of software packet processing systems.
Wait. Have we seen that talk already? Yeah, right? That guy is very familiar. It's he reminds me of the talk about network cards, right? Let me quickly check that before I think it's a different talk, but maybe there are some overlaps. Demystifying network cards. How could it explode when I'm not here? And why is my scrolling inverted again? Wait. Demystifying network cards. Paul Emery. And here it is. PhD student. What?
To this talk, and these are all.
It's Paul Emmerich again. Okay, so it's the same dude, but it's a different talk, and we saw the, like, so to say, introduction already. That's fine. I think it's, yeah, that's fine. Cool. Yeah, then let's continue.
With me today, Simon and Sebastian. We speak that. So a quick talk about packet. I'm a PhD.
He also used the same phrase of like. He also mentioned that he's very fast at speaking and he is sorry for the translators and so on. Yeah. Okay, but whatever.
Technical University of Munich, and I'm researching performance of software packet processing systems.
Yeah, and performance, that was his thing.
Today we are going specifically to talk about network drivers. Well, why look at network drivers as a case study? Well, it's obviously our research area, so it's the next best thing to do. And also user-space network drivers are all directional, and user-space drivers is where you can use all the fancy languages. I have already talked about user-space network drivers here last year, so a quick recap of what I presented here last year is about the IXI project. And the IXI project is a thing I started where I wanted to show off how you can write a user space driver that is actually readable and understandable and fast at the same time. So the goal is this to be used for educational purposes. It's around 1,000 lines of C code that's full of references to datasheets, specs, and so on. And well, if you want to know more about that, watch my talk last year. Just a quick diff. Since then, we've added support for real ionics, and we've now a vagrant setup, so you no longer need real hardware to play around with that. You can check it out on GitHub. Yeah. Then I wrote it.
Oh, okay. Yeah. So he mentioned the talk we saw yesterday. So he mentioned, if I remember correctly, that he was planning to support virtual architectures, and it seems like he actually did that. That's cool when people do what they plan. It's very nice to hear that. So that seems to be some follow-up talk. That's nice. Okay, it's fine.
C back then, well, why would you write a driver in C? Seems like a kind of obvious question. Why wouldn't you? Because most drivers are written in C, and if you're going for educational use of the driver, then might as well use the language that all the other drivers are in. It's also the lowest common denominator of all the systems programming languages, meaning everyone should be able to read C, and I also think that C code can be quite beautiful in some cases. Can we get a quick show of hands who here thinks they can read C code? So this is way more than expected.
Easier than C++ code, mate.
But like basically everyone raising their hands. So let's have a look at some C code. This is some this is some actual code from our driver that was added by a student, and when I initially got the pull request for this from my student, I was like, well, no, we can't add this macro. It's like the goal was to have readable code. You can't add this. And then we discussed it a little bit. In the end, we ended up adding it to the code base because it's really necessary. There's no better way to do this than this macro in C. Who here knows, who can immediately recognize the macro and knows what it does?
Okay, let me try, boys. I have no idea. Wait. It's called mystery macro, so he probably changed the name. So it takes a pointer type and a member, and then type of type. What? It's dereferencing? What is the 0 doing there? I have no idea. What the heck? Member? What? I've offset off? I've no clue.
I see one hand. A few hands, okay. Not bad, not bad. Does it help if I show you the actual name? Anyone who recognizes this macro?
What is the name? I want to
Some
see it.
more hands, yeah, okay.
Show me the slides.
Still, this is kind of little bit
Container of. I still don't get it.
Or a little bit to abstract drivers. It's commonly used in drivers to abstract the different drivers. I've macros copied from the Linux kernel, and I've searched through the Linux kernel sources and found 15,000 users of this macro, so it's not at all unusual to have C code like this in your driver. So I then agreed to add it to the code, even though probably almost no one can read it. The actual code also has a comment to a blog post that explains what this macro does. But it also shows the problem that maybe a lot of people think they can read C, but then they encounter something like that, and suddenly, yeah. Point is, it can be ugly, and it can not only be ugly in terms of how it looks or feels by programming, it can also be ugly when it comes to security properties or security issues. This is a screenshot from cdedetails.com. No, I don't expect you to be able to read all these figures, but basically it shows there are security bugs in the Linux kernel. This is specifically all the Linux kernel bugs found in the last 20 years or so. And now, you can say, well, why is the language to blame? You can write bad code in any language. And what we now would have to do is basically...
Except Rust. True fanboy. No, like, as always, do not take anything seriously what I say in these advertisement streams. This is just to advertise the server, and I like to watch these talks to entertain myself and trash talk a bit. So yeah, what do I know about Rust?
We would have to go through all these bugs and check whether they could be prevented by using a memory safe or a better language, and it seems like a lot of work, but luckily someone else already did that. Last year there was a paper by Katza et al. Who developed a operating system in Go, and they looked at all code execution bugs in I think 2017 in the Linux kernel, and looked through all of them manually and tried to figure out whether they could have been prevented by using a different programming language. For 17% of them they weren't sure, because it's a kind of weird bug and they couldn't tell whether it could have been prevented. For 22% that were clear logic bugs, that clearly you would have made that bug probably in any language, and the language wouldn't have helped. But for over 50% of the bugs were related to memory, both use after free, out-of-bound accesses, and so on, and these can be prevented by using a better programming language. Now, these are 40 preventable bugs in this case study, and we looked at them to figure out how many of these bugs were in drivers versus bugs in other parts of the kernel, because we are specifically looking at drivers. Well, 39 of them were in drivers. The other one was in the Bluetooth stack, and of the drivers, the Qualcomm Wi-Fi driver had 13 bugs. Yes, I know, I was shocked. Bugs in the Qualcomm Wi-Fi driver. Who would have thought? Now, based on these results, should you be writing new code in C in 2019? Well, probably not if you have a choice, but you just often don't have a choice. If you're writing some kernel code for some reason, sure you can write a kernel module in Rust, but good luck getting it upstreamed. And other languages are like, good luck writing a kernel module in JavaScript. It's probably not going to work. And if it's going to work, it's probably a bad idea. Now, this is why we are looking at user-space drivers, because they can be written in virtually any language. So we are not constrained by any environment here. And the question would now be, are all the languages an equally good choice? Can I do it in any language? Should I do it in any language? Which language should I use? Is a JIT compiler or garbage collector a problem in the driver? Now, I initially wanted to write one driver in one high-level language to have a case study and then extensively evaluate it. But then I thought maybe it would be a better idea to write drivers in all the languages. But it turns out I don't speak all the languages. But luckily I could recruit the help of a few students, and this is a screenshot from my website at the university where
Network drivers Go, Rust, Java, C#, Haskell, Scala, OCaml, JavaScript, Python, Bash. Love it. Oh my gosh, network drivers in Bash. Isn't that essentially C? Because in Bash you just call the Linux system calls directly, and this is like kinda C. Oh my god, I want to see the driver in Bash, man.
Added announcements for writing network drivers in Rust, in Go, in Java, in C#, in Haskell, and so on.
And so on, come on! I want the audience reaction to the Bash one.
Then at first my colleagues at the university looked at me in weird ways and were like, are you serious? You realize it's the same announcement all over again? Some of them still can't tell if I'm serious about this, but yes I am. And I got a lot of response from students. I think I talked to a total of 30 students or so who wanted to do one of these theses. And then these two were one of the first ones to talk to me, and I tried to scare them all away initially. I told them all, it's going to be really hard, you can get an easy thesis, it's probably not a good idea, you need to know a lot of low-level stuff. And so I scared away 20 of the 30 I talked to. In the end, we did 10 theses, and yeah, it's quite nice results so far. A few are still ongoing, but I hope we will have 10 different languages for drivers soonish. I think finished depending on how you count, finished is 6 or 7. And yeah, also turns out giving a talk here is a really nice way to recruit students, because a lot of my students mentioned that they saw my talk and contacted me afterwards for thesis. Now, what did I tell my students? How to go ahead to write a driver? Well, I explained to them basically the very basics of how to write a real estate driver, how to talk to a modern PCI Express device and what you need to do. Basically, there are 3 different ways to talk to modern PCI Express devices. We are ignoring a few legacy things here, if you like. Yes, old I/O instructions not on here, sorry. First way to talk to a device directly, simplest way is memory mapped I/O. Memory mapped I/O is just a magic memory area that is mapped into your process and directly goes through to the device, and if you write that memory, the device gets the request and can reply to it. That's usually used to expose device registers. On Linux, you can just embed a magic file via the DIO framework, and then you have access to that from your user space program. Second way is kind of how the device talks to you, or how the device talks to the rest of the system. That's direct memory access. That is just a way how the device can read and write arbitrary memory locations. And for user space drivers, you just have to figure out where our memory address space is mapped physically. Then we can tell the device to write something there, and then it will just show up in our process without us having to do anything in the kernel. And the third way are interrupts. We will not be using interrupts here because we don't need them for a high-speed network driver, but I have it on here because sometimes people say, well, you can't use interrupts from a user space driver. That is incorrect. You can use the VFIO subsystem that has protocol for interrupts, but we won't be using them here. Now, what did I tell my students about how they should go to write their drivers? Well, basically, they should just remove the current kernel driver, do the magic mmap call on the right magic file, then figure out the physical addresses, and then just write the driver. It's really easy. So, then we have a lot of hardware at the university, and access to servers with 10 gigabit network cards of the Intel IXGBE family. This is a really common network card that you will find on a lot of servers, like the default go-to 10 gigabit network card on any servers. You will often find it on board or embedded in one of the CPUs. Even the nice part about this, it has a very, very nice datasheet publicly available that documents basically everything. Fun fact, we found it easier to program against this hardware black box with a good public datasheet than we had to implement the DIO spec, which is an open specification, has several open source implementations, but yeah. Then this network card is a little bit older, 10 years old or so, and it has a nice property that it's still very low level compared to newer network cards. If you implement this on newer network cards, you are usually just exchanging messages with some firmware, and that's just boring because the firmware implements everything. Sure, the older network cards also have some firmware, but you get a lot of more low-level access to the card, and you don't feel like you are just talking to a firmware. You feel like you are implementing an actual driver yourself. So now, these were the basic things I told my students. I will now give over to Sebastian, who will show a little bit of C code about, well, how to write a code, how to write a driver in C, and whether that could be done in a high-level language.
Thank you very much, Paul. We just showed you what we have to do in general. I'm going to take a bit more detailed look at this. So first of all, of course, we have to figure out our PCI addresses. You can do this via lspci, and then you get a list of all the PCI devices, and you just look for something like Intel Corporation 82599, something that looks like this. And then there at the front of the line, similar to a MAC address, and well, that's the address we need. So now we got the address. With this address, we can just go there and unload our driver. That's basically it. You just write there. Next step, we have to mmap our PCI register from the address space. And for that, we open our magic file and execute an mmap. The challenge here is mainly that for every high-level language you have to have some kind of way to actually use an mmap, either via a library or, in the worst case, you just have to use some SQL for that. Next thing, this is an extract of the datasheet. In the datasheet, it's basically like this. You have the register name, register offset, and then you can just go through the whole document and find all the registers you need to read and set the things for the driver. A quick example. Network cards have LEDs often, and we can make them blink, turn on and off. And how do we do this? Well, we have to get the base address of our registers at the offset that we found in the datasheet, and then just switch the bit, and this turns the light off and on. And right this back of course, the register. Also, this is one of the very few valid uses of volatile in C, because we have to really prevent compiler optimization here, as we have memory access from multiple sources. Next step, how do we handle packets via DMA? Packets are transferred via queue interfaces. The receive queues, transmit queues, and these are often called rings because, well, they are organized in a ring-like structure. These rings are configured via lmao, and when this is done, we can access the device via DMA. These rings then usually contain pointers to packets, and these packets are then also accessed via DMA. The details vary a bit between cards and devices, but that is not unique to NICs, this process. This is pretty much the same thing for all PCIe devices. They all kind of look similar. So, what are the challenges for high-level languages? We have seen some, for example, the mmap call. We somehow have to get access to this with the proper flags. Another thing, we have to handle externally allocated memory and the layout this memory comes in. Also, we've seen we need volatile to prevent compile optimization, so we have to have some kind of semantics so we can enforce this in other languages. And of course, often, especially for low-level stuff, you often have to use some kind of unsafe code for high-level languages because, well, many operations are inherently unsafe when you operate here. But we try to contain this unsafe code to as few places as possible to contain this to a small area. Okay, now some basic challenges. I'm going to hand back over to Paul, who says something about the goals for our implementation.
Okay, basically this is what I've told my students about what I'm expecting for these implementations. I wanted to have the same feature set as my C driver, which was kind of used as the reference implementation, and it also was supposed to have a similar structure, but at the same time we wanted to have code that looks like it was meant to be written in that language. It's always a difficult trade-off to use safety features wherever possible, but if they cost too much performance, do we really need them in all the places? Where can we use the safety features? Where do they make sense? And then we wanted to quantify that. The idea is to really have, in the end, like 10 driver implementations that we can quantitatively evaluate and look at the performance of all of them, look at the safety properties of all of them, look at properties like safety for memory accesses is guaranteed, for packet buffers, yes, no, for other stuff, yes, no, and so on. And I'm now going to look at a few of these languages. Basically, I'm only talking 1 or 2 minutes about each of the languages for students who are not here but have already finished their thesis, and then we are going to have a deeper look at Go and Rust. But I will now start with the other languages where it's only a very, very short high-level overview. Well, the first one is C#, which seems a little bit unusual, but we found a student for that, so why not? And no, we didn't develop a driver for Windows. Microsoft's core CLR is available on Linux and works really well. For those who don't know C#, C# is a just-in-time compiled, garbage-collected, memory-safe language.
It's
and
just
it
in
has
time?
a relatively obscure or rarely used unsafe mode, and unsafe mode features full support for pointers. So you can basically write code that looks like C, you just have to give the compiler a special flag to tell it, hey, I'm going to use unsafe stuff. Then how can we access external memory or foreign memory? There's, for example, there are a few nice wrappers in C# with pinvoke or the unmanaged memory stream and so on, but that turned out to be too slow for our implementation, so we used that unsafe mode, which basically looks like this. You see the unsafe keyword here, and the other stuff just looks like C, and it also feels like C when you are writing it, so it's a really nice language to write the drivers. And again, the unsafe code is contained to a few well-known places that can then be audited, compared to a C driver where the unsafe code is all over your code base and you don't know where the bug is. Here we know if there's a bug, it's probably in there that we have, well, not checking the buff size properly or something. And okay, that's all it is for C#. Another unusual language for drivers is Swift. Also found a student who mentioned, well, can I do it in Swift? I was like, oh, I didn't even think of Swift. Sounds like a good idea, yeah? So no, we didn't develop a macOS or iOS driver. Swift is also available on Linux. Swift is a compiled language. It's compiled via LLVM. Memory management is done via reference counting. There is no garbage collector, and it's mostly memory safe. Now, you again have to use some kind of pointers. There's unsafe buffer pointer, there's also unsafe raw pointer and more classes. And we are using these things to make packets that are stored in the DNA buffer available to the application using the driver. And for example, here's a property that wraps some memory in a unsafe buffer pointer wrapper, and the unsafe buffer pointer wrapper forces you to specify how big the buffer is, and then it does the bounce check for you when running in debug mode. Then pointers are kind of a little bit more verbose compared to C#, but basically you can use them like pointers, and operator overloading here can help for some of the other managed buffer pointers, raw buffer pointers. There is already an overloaded operator, so it looks like an array access, but yeah, totally possible to do that in Swift, even if you are writing a driver instead of a UI application. Now, for the science of functional programming, we have a fully working implementation in OCaml. OCaml is a compiled language that has garbage collection for memory management. It's also memory safe, and it's the first functional language we are going to look at. And one nice quick feature of OCaml is the cstruct library. The cstruct library allows you to specify memory layout like this. It kind of looks like a cstruct, and then it generates from that code for accessors, and this is really nice compared to the Swift example where you would have to hard code the offset somewhere, and it's much nicer to have this kind of code generator here, which does the right thing for you, and also can do automatic endianness swapping and so on. And then the code in OCaml now looks quite different compared to what you might expect for a driver code, and this is, for example, just a function that counts how many packets has been received in the receive ring by checking the flags, and we can see here that we are using the get at rxwb status, which is the getter function from the previous struct declaration. We are checking a flag in that, and then we are just counting the packets, and then we know, okay, we have received 10 packets or whatever since the last call to that function, and we can now pass them on to the user of our driver. More functional programming. We also have an implementation in Haskell. Haskell, again, compiled language, memory management via garbage collection, memory safe, and also functional. Few nice features of Haskell that you might not know about is the system POSIX memory package has a lot of really helpful functions. This is compared to OCaml, where we had to write some C code to get mmap and mlog with the right flex working. And here there was everything available, and the foreign package has nice functions like peek byte, poke byte, and so on, that you can just do a raw memory access. And another thing we are using in Haskell quite a lot are the sum types, because A lot of things in the drivers are where you have in C a union. There's basically this part where you write some data in a DMA buffer in some format. The device reads this data in the like for the transmit packet descriptor. We have the transmit read format, which looks one way. Once the device has transmitted the packet, it goes back to the same memory location and overwrites it with a different thing, so we then need to read the same data as something else, and it's basically a fancy C union, and this is a bit nicer to work with than the C unions. Okay, these were the languages of students who are not here this year, and you can check out all the implementations on GitHub. There will be a QR code to scan on the last slide. And I'm now going to hand back to Sebastian, who's going to do a deep dive into Go.
Yeah. Thank you very much. So now we've seen a few languages. Next is up with Go. What is Go? Go is a compiled programming language. It's been developed by Google. It's generally a general purpose language, but as it's been developed by Google, it's mainly designed for distributed systems because that's what Google does. Distributed systems. A driver is not a distributed system, so why should we even use Go? Well, Go does offer a few things that are quite nice. It has a runtime that has a garbage collection and also enforces memory and type safety. Also, it has a very large standard library, so we don't need to use any other code except standard library code. So, how do we program drivers in Go? Actually, in most cases, it's just like C. There are a few main differences though. On one hand, we don't have pointer arithmetic. We have pointers, but we don't have arithmetic. And this is what we need for managing our DMA memory. And the second point is we don't have a volatile for the memory barriers, for our register accesses mainly. So what do we do instead to compensate for that? First of all, we can manage the DMA memory via slices. That's pretty easy. And the second thing is we can use unsafe pointers for pretty much all the rest. Unsafe pointers are arbitrary pointers, so that's good, but they do circumvent the runtime, so we have to be careful with them. And this is what we use for mainly physical address calculation and register access. And there is also a rule set for unsafe pointers, so they're still valid, and of course we follow this rule set. So, two quick examples. First of all, mempools. Here you can kind of see how we manage the DMA memory. First of all, we allocate the DMA memory, initialize the mempool, and then this mempool.buff, this is actually the whole memory map area. We can just subslice this into packet buffers, so you see that's pretty easy. Next thing is for physical address calculation. This is where we need our unsafe pointers for the first time, because we have to translate our virtual addresses into physical addresses that the network card can then use to actually send and receive packets. And for this, because the runtime checks many things and you have to explicitly convert types, you first have to convert your pointer to an unsafe pointer, and then you can convert it to an integer type, the UN pointer, and yeah, it's how you do this in Go. Also, no volatile, no problem. Instead, we need a volatile, as we share registers with the network card, and we need some kind of compiler memory barrier to prevent reordering. We don't have volatile in Go, but SIG atomic functions do prevent reordering amongst other things. They provide stricter guarantees than volatile, but yeah, it doesn't really cost us any performance here, so we're just going to use that. And yeah, so we can use atomic store and load for integer types to then get our memory barriers. So, as a conclusion, I thought Go was actually quite nice to work with. the safety properties have been proven. Cutler et al., as Paul said before, wrote a kernel in Go, yeah, so it is safe. It gets you some safety guarantees. And the other thing, it's kind of a personal opinion, but I think it looks like C code in beautiful. But it also has downsides. In the best case, it's approximately 10% slower than C, and as you get to more suboptimal cases, it's even worse compared to C. But yeah, we have to live with that. Also, the descriptor access can be a bit ugly, but well, as long as it works. So next, I'm going to hand over to Simon, who did this in Rust.
Thank you, Sebastian. So let's talk about Rust. What is Rust? Well, the Rust website says it is a safe, concurrent, and practical systems language. Sounds great. That's exactly what we need to write a user space network driver. So is there anything else we should know? Well, yes, Rust has no garbage collector, so we have less overhead for memory handling. It has a unique ownership system and some rules for moving and borrowing values. With these rules we can accomplish Rust's goal of memory safety, and we have unsafe like in other languages presented before. What is the ownership system? Well, it is the core feature of Rust. Actually, it's basically just a set of three simple rules. Rule number 1, each value has a variable that is its owner. Rule number 2, there can only be one owner at a time. And rule number 3, when this owner goes out of scope, the value is freed. These three rules combined with the rules for borrowing values keep us safe from memory bugs like double freeze, and as they are enforced at compile time, we don't have any performance penalties at runtime, so our programs are similar to C programs, but we have the great advantage of memory safety. What does it look like in our implementation? Well, we have packet structs for our network packets that own DMA memory, and these packets are passed between the users of our driver and our driver, and with them along, ownership is passed as well, and that's pretty cool, because when the packet is passed to the user, only the user can modify the packet and the packet content, and when it's passed back to the driver, only the driver can modify it. So we have basically safe packet handling, unlike in other languages. And at the bottom of the slide, you can see how you would use the driver based on our driver's interfaces. You can see how to receive, modify, and send packets. And yeah, there's no way to screw up. So, for example, you cannot forget to free packets, because packets are freed automatically when they go out of scope and are returned to the memory pool of our driver. So, yeah, this is safe code, and there's nothing you can do wrong here. But unfortunately, we also have unsafe code in our driver. What is unsafe code? Well, not everything can be done in safe Rust. For example, calling foreign functions and dereferencing raw pointers is unsafe, but this is nothing unusual. The idea is to reduce unsafe code to a few places and do some checks to make unsafe code safe. What does it look like in our driver? Well, for example, we have the set register method to set the registers of our device, and we use pointer write volatile to write to some register of our device. And before we do that, we have some assertion in our code to assert that the address we are going to write to is indeed inside of the map memory region. So we have some great code, but is it fast? Well, to find that out, we set up a testbed to benchmark our drivers. We have two servers, a packet generator and the device under test. They are connected bidirectionally with two 10 gigabit per second connections. We use the Munchen packet generator written by Paul, because obviously it's the best packet generator. Yeah, and on the device under test, we have a simple bidirectional packet forwarder that we implemented on top of our drivers in all languages. And yeah, so let's look at the results for our measurements. So this is a graph showing the throughput of our forwarder. On the x-axis you can see the CPU speed, on the y-axis the packets per second. We look at packets per second because the main overhead is per packet, not per byte. And the top of the y-axis is 30 million packets per second, because that's about 20 gigabit per second at minimum size packets. You can see the different plots for the different languages. It's linear scaling with the CPU speed. Rust is the fastest. Swift is, yeah, well, it performs incredibly poor. And so the thing is, usually you don't manually change your CPU speed. So we asked ourselves, is there anything else we can modify? Yes, there is. You can change the batch size, so how many packets you send at once to the PCI device, because that avoids some overhead. And kernel drivers usually use a batch size of 1 on transmission, and higher batch sizes are one of the main reasons why user-space drivers are faster than kernel drivers. Batch size of 32 to 64 packets is a very good batch size, because higher batch sizes are bad because we have more L1 cache misses. And well, we asked ourselves, why does Swift perform that bad? And Paul is going to tell you why it is like that.
Yeah, so if you have some program that is performing not as expected, well, what do? You run some profiling on it, and then you get a lot of data, and then you need some way to visualize this. Common way to visualize profiling results is this thing called a flame graph. Basically, the x-axis is time spent in a function, and the y-axis is the depth of the call stack. And no, I don't expect you to be able to read all of this. These are just the function names that are in here. And if you look at the topmost functions here, these are the leaf functions where the time is then actually used. And we can characterize all these functions, what it's doing in there. And well, we found out it's due to Swift's memory management. Swift adds calls to the magic internal least retain functions for each object used in each function, just to keep track of the reference counting. And that's, well, basically no problem if you're just writing a UI up with some buttons or something, but if you are writing a driver that has to pass through millions of packets through a lot of functions all the time, then it turns out it spends, well, 76% of its time in these release retain calls, so it could be 4 times faster if it had other way to manage memory. And for comparison, in Go we spend less than 0.5% in the garbage collector, because it's, well, a quite simple application. So now the big advantage of having these semantics with reference counting in Swift is, of course, that there are no unpredictable pause times, and the garbage collector in Go might just stop your driver for all the time or for some time. The question is now, is it a good idea to have a garbage collector in something like a driver? Now, the good thing is we can measure that because we have this forwarding application, and we did that. We measured the latency of all the packets that we forwarded. This latency was measured at around 16 million packets per second. And what you see here is the cumulative distribution function of the latency of Rust. And this is basically an almost perfect normal distribution centered at around 8 microseconds, which is a very nice result. For comparison, a hardware switch takes around 1 microsecond to forward a packet, but 8 microseconds is for a software forwarding thing is really nice and fast. And now to the same graph, let's add the other languages, and now we see, well, Go is kind of similar, but C# is a little bit slower at the top. But I do realize that this graph might look a little bit confusing, so let's really quickly explain it how to read it. If you are not familiar with these CDFs, now we look at a value at the y-axis, for example 0.5, so 50%. Then we go over to the language, go down to the x-axis, and that just means that 50% of the packets take less than 8.9 microseconds to be processed by C#, and the other 50% take more. So then looking at any latency where a garbage collector or unpredictable spikes are involved, then it's always a good idea to not look at the median, but at something like the 99th percentile. And for C#, 1% of the packets take longer than 30 microseconds, and 1% of the packet is a lot if you're processing a lot of packets. like 1 in 100 packets, and you're doing millions of them per second, so you are going to get these worst case latencies quite often. What we really want to know is not the 99th percentile, but the 99.9999th percentile or something like that. So we will need to zoom into that graph here. If you are zooming into a graph, you usually change the axis to be logarithmic to zoom in. Well, in this case, it would zoom into the wrong part of the graph. So we also have to subtract the axis from 1, yielding the complementary cumulative distribution function on a logarithmic axis. Now this is inverted and a little bit a confusing graph, but this is what you would see in an academic publication talking something about latency or anything like that. But I think it's a really confusing graph, but it has the left side and the top, or the bottom line would be the latency of 1 packet in a million packets. What we can do with this graph to make it a little bit more approachable is we can basically just rotate it and change the axis description of the x-axis, which was the y-axis before, and the x-axis is now the percentile and the y-axis is the latency, and now it's easier to read. We can, for example, look at 99.99 and check out where it's, which latency at the percentile is for the different languages, and this is a kind of graph that you will see for a lot of latency evaluations of anything that has latency spikes if done properly. You unfortunately often see people doing latency evaluations and then providing like the average or median latency, which is for many cases a completely useless value. Most of them probably just don't know better, but if you want to evaluate latency, please have a graph like this in the end. There is if you want something to Google, there is the library called HDR histogram, which can generate these graphs from latency measurement data, and that's just a really nice way to characterize garbage collection or just-in-time compilation latency or anything like that. Now, we got a driver that is nice and fast and has a relatively low latency for most languages, but we have not yet really looked at safety and security beyond what was offered by the language, because our driver still runs as root, like all or virtually all user space drivers run as root by default. And well, why is this the case? Well, I've shown this code before. There are a few operations in the initialization that just require you to be root, like mapping the PCI Express resource requires you to be root. For implementation details in the Linux kernel, we need non-transparent huge spaces for the DNA buffer. They require you to be root to allocate them. Locking memory requires root. So these are clearly all functions related to initialization or setup. So the obvious idea is, well, write a small program that does that for us, keep that simple and audit that and check that it's good, and then drop all the privileges. Can we do that? Yeah, sure, we can do that. It's relatively easy, just drop privileges after setting up memory, but that's still not really secure in any way, even though you're now running as an unprivileged user. And to understand why this does not work as you might want it to work, we have to take a high-level look at how memory access works on a modern system. And this is what a modern system looks like at a very high-level view. We have the CPU here at the top with our application running on it. And in the bottom left, we have the Express device. Bottom right, we have some memory. And if we now want to do some memory access from our application, it goes like this. It goes through a thing called the MMU. The MMU is the memory management unit. And the memory management unit translates your virtual address that you have in your program to a physical address that can be used by the memory controller. Now, the security or the isolation between processes is controlled by this MMU, and only the kernel can reprogram to the MMU to guarantee the isolation. Now, if we want to access our device via PCI Express, for example, memory maps.io, it also goes through the MMU. The MMU then knows this is not going to memory, but to PCI Express. It talks to the device, and it's also all fine. Now, you could argue clearly these are the two kinds of memory accesses we do. Both are checked via the MMU. So what's the problem? Well, the problem is that when we tell the device to do something with memory, as previously mentioned, we tell the device physical addresses to use them, and well, of course, the device does not go through the MMU because it doesn't know, it doesn't have a concept of its use by a processed or it's being used by this kind of process. It just has full access to all of your memory, and so if you somehow own the program that is running as an unprivileged user, it's quite a trivial exercise to get any data from the important area that you shouldn't be allowed to access or write any data there by just telling the device to do it for you. Meaning any application that has direct access to a PCI Express device is effectively root, even if you drop privileges. So the obvious solution is to somehow make this access path go through the MMU, and there is this fancy hardware component called the I/O MMU, which is exactly for this use case. This can be found on any modern CPU that has hardware virtualization features, because it's mainly being used to do pass-through of PCI Express devices to virtual machines in a safe and secure manner. But you can also use it for user space drivers. You just need a way to tell the kernel to configure the I/O MMU with the proper restrictions for us. And then the access looks like this, and we just need to configure it in a way that the I/O MMU has the same permissions for that device like the MMU has for our user space program, and then it's perfectly secure if you're a program that's owned, and it doesn't have any privileges beyond what your process has. And this is also useful for safety, because when I initially wrote the driver, I kind of killed a server when I apparently misconfigured the email and overwrote something that was important for the file system apparently, and then it was dead and I had to reinstall it. So that wouldn't have happened if I had started with the I/O MMU in the first place. How do you do that? To use the I/O MMU specifically on Linux, which has a nice subsystem called the VFIO subsystem, and this is what we can use. We just need to prepare the system as a root. This is a one-time step as root. We can bind the device to the VFIO driver instead of to no driver at all. We can change the owner of the resulting magic device file and pass it to an unprivileged user. Then we have to give the unprivileged user permissions to lock memory to allocate DNA memory, but we can also restrict them. You are allowed to allocate 512 megabytes of locked DNA memory, and then all the remaining steps can be done as an unprivileged user. The unprivileged user can now call an mmap on the new device, and then the unprivileged user can communicate with the kernel via I/O control commands on the magic device, and it can also tell the kernel to please allocate DNA memory. Also actually a better way to allocate DNA memory for technical reasons. And then you can just use the device as you had before, so you just need to change the setup steps. And then you have a user space driver that can run with, well, no special privilege at all. And the I/O MMU will check all the accesses, and the kernel will make sure that you can't configure the I/O MMU in a wrong way. You can just tell it to please configure the I/O MMU in such a way that the device can access my current address space, but not anything else. And we have implemented this in our C driver. My student who implemented this is actually here today, but he was afraid to come up on stage. But if you have any questions, you can talk to him afterwards there.
What the fuck?
Now we have this awesome driver which is safe, secure, and everything, and yet some people still argue user space drivers are useless. I already have a driver in the kernel. Why do I need another driver? Why would you want to write a driver? And obvious answer to the question is, why wouldn't you want to write a driver? It can be fun. I had a lot of fun when I wrote the first driver. So
okay.
Yeah, then maybe you just need a quick and dirty driver for a weird device that you found somewhere. Maybe you just need quick development cycles where you don't want to shoot down your kernel all the time or reboot all the time. If you have a weird device that you are developing with, maybe you're developing a custom device, maybe you have some FPGA board that you want to talk to real quick without being involved in some kernel stuff. Or maybe you just need a feature that's found on the hardware but not yet on the device driver. There are some features. There's like a lot of stuff in the past. We have internet IPsec offloading, which wasn't in the open source driver, and so on. But something we have done recently is hardware timestamping. The latency measurements I showed before required us to take timestamps of 15 million packets per second with nanosecond level precision, and it is quite hard, and people usually use special hardware for this. And we ourselves have used net FPGAs in the past for this, which well, can be a lot of fun to use these nice devices, but at the same time it's prohibitive from a cost perspective or from a user experience perspective for some people who just needed to take some timestamps. So we want to do it on some cheap off-the-shelf commodity network cards, and turns out all of these, or some of the newer cards have a hardware feature that can just add a timestamp to the incoming buffer of all packets that they receive, but sadly none of the existing drivers supported this feature. But I've shown you how you can access registers. You can just skip the step where you unload the original driver. You can just just nmap the thing while the original driver is running, poke the right register in the right way, tell it to do this please, and now you got a timestamp at the end of every packet. Sure, it probably breaks your TCP stack or whatever if there's extra data, but like PCAP doesn't care, or in this case you just did it with DPDK and got the raw packet buffers, and it also doesn't care if the device thinks there's 4 exabytes or 8 exabytes. For this setup that we had here, we used the embedded NIC on a CMD, and we had a fiber optic splitter to sample timestamps of all the packets before and after the bypass test, and then
what's wrong with you, mate?
with the measurement of all the things. And yeah, so this is just a simple use case why you would want a driver. To conclude, I can only really say that I think drivers should be written in better languages now. I think you shouldn't start writing a new user space driver in C nowadays. Sadly, if you look at the world of user space drivers, there is mainly DPDK, which is a network user space driver, it's all C. There is all C because it's mainly copy-pasted from kernel drivers. Then there is SPDK, which has NVMe drivers, also all C, and the big exception to this is Snap, which has drivers in Lua, which is quite nice. And well, our implementation which has lots of different things, and we really want to compare these other these languages. You can scan this QR code or just Google for XC languages on GitHub or whatever, and then there's like this meta repository that has links to all the implementations, will have a link to this talk, and yeah, basically check it out, write your own driver, no kernel code needed. Thanks for your attention.
Thank you very much, Paul, Simon, and Sebastian. We do have time for questions. Please line up at the microphones. And to get it started, please a question from our signal intro from Internet.
So the IRC, first of all, was wondering why was the BASH proposal only offered as a bachelor thesis?
And why is it not shown in the talk? That's my question.
Yeah, the BASH question kind of expected as well. Like about adding random language and so. Well, why can't you do it in BASH? The problem is, I tried to implement it in BASH. It doesn't work the way I wanted it to work.
Oh, so it's not Finnish actually. So it was a scam that it's on the slide. Oh, wait. Were the languages on the first slide just like suggestions, and nobody took the suggestion and wrote a thesis about it, and not actually finished projects. That I might have misunderstood that one. Okay, that's all. Also, why there was no Haskell, probably because that was also on the slide and it wasn't mentioned. Yeah. Okay, I probably misunderstood that one. Sad.
I would need to write more C code. The way I tried it does not work is I wrote a short C program that called the mmap thing and then just slept forever. And then the idea was to to access the address space of that program that just called the mmap via the procfs system, and then there's like this magic thing that has all the things, and then with DD you can write and read from there. But it breaks at some point, because it goes through when reading, but if you write something at some point via procfs, that doesn't go through the CCS. So it didn't work, and I only wanted it as a bachelor thesis because kind of a master thesis should maybe be a little bit more serious than a joke driver.
Hey, Bash is no joke.
Yeah, maybe a more serious one. Gordon is asking how to use the chest to handle interrupt requests or code with strict timing requirements.
If I have strict timing requirements, I'm not going to use interrupts. Interrupts are horrible. If I have strict timing requirements, I just poll the device all the time. This is how basically all user space drivers work. They just ask the device, is there a new packet 1 million times a second? interrupts are one of the slowest way to communicate between CPU and device. Just receiving the interrupt requires you to do a context switch on the CPU, then you have to do a context switch back because you don't want to do too much in the interrupt handler, and then you have to call the device anyways because the interrupt just tells you that something has changed. So if you really care about the latency, then you just call the device all the time. And for user space interrupts, check out VFIO, the VFIO framework. You can reliably call on something and then you get notified if there's an interrupt if you really need that.
Okay, let's go to the hall questions. Please keep your questions to one sentence only and only ask questions because there's many of them. Microphone number 2, please.
So when you compare different user space drivers in different languages, why was Rust slower than C, given that the memory safety is compile time?
Yeah, well, we have a few more memory operations because of the safety. So we have to move the packet structures from inside the driver to outside to the user, and you don't have that in C. So Rust was a bit slower because of that. But I think you could optimize it maybe a bit better because, yeah, well, it was just a bachelor's thesis, so I didn't have that much time. But yeah, I guess it could be a bit faster, but I think it would still be a bit slower than C.
Also, my C driver doesn't do any bounce checks at all, just expensive.
Microphone number 3, please.
You mentioned Haskell in the beginning, but it wasn't in the comparison. Can you talk about that?
Haskell is not yet optimized for performance. It would have been unfair to add an unfinished version for it. It's currently still quite slow, and I didn't want to add it there.
Microphone number 4, please.
Awesome talk, thank you very much. Have you considered using total programming languages like Idris or Coq, where your compiler can check the logic of your driver?
What languages?
I don't have a student for that to implement it, but yeah.
Microphone number 1, please.
Okay, I've seen several languages with garbage collector included, including those. So my question is, how often do the GC stop the war happens, and what is the general heap sizes?
How often? I don't know how often. The latency showed you how long it takes, which was like up to 40 microseconds, which depending on your application might or might not be a problem. There's a few other data from, we referenced this paper of the guys who implemented a whole operating system in Go. They mentioned they see up to 200 or 300 microseconds of source times and heap size.
To be honest, I didn't measure heap size. Maybe something about the garbage collector. I'm not even sure if, how much it actually works because the Go profiling just dropped this node as it was so little time compared to the others. So it's basically irrelevant except for probably some latency.
Microphone number 3, please.
Yeah, I missed a couple of languages, OpenCL and CUDA. Not because they're particularly interesting languages, but it would be interesting to have the GPU talk directly to the network.
There is a paper out there that's called Packet Shader thing. Yes, they do exactly what you There's also another paper out there called Raising the Bar for GPU Packet Processing or something like this. They basically argue against that. The main problem is if you are transferring the packets between the network card and the GPU, this is kind of slow and you need to use gigantic batch sizes. The packet shader guys used, I think, batch size of 4,000 or 8,000, which affect latency, and they don't have a proper latency evaluation. Wonder why. But if you're interested in GPU packet processing, read that packet shader paper.
How do you deal with I/O ordering? The x86 will guarantee you that the order in which CPU posts I/O accesses is the same as the device receives them, but on other platforms this is not the case.
Yes.
And if you do it with UIO, the UIO doesn't give you any such guarantee.
Well, for memory ordering, it's highly specific to the device you're using, which memory ordering semantics you're using. The weird thing is in the device we are using here, the Intel device, there is one location where I'm so really sure that I do need a release memory order semantics because there's something which clearly sets some flag and then the device reads some other memory data. And like 99% sure that this should be release memory order there, but none of the driver implementations has any release memory order area there. So we don't need it here. And other than that, for Go and Rust, we of course have low-level primitives to ensure or to enforce hardware memory barriers. For other languages, if you, for example, check out the snap driver, which is written in Lua, they have a little C stub which calls write M10 instruction at the right place.
Thanks.
Number 4, please.
Thank you. The abstract of this talk mentioned that the user space C implementation was 6 to 10 times faster than the internal implementation. Was this just because of the batch sizes, or were there other reasons for that?
So this is mainly due to the batch size. The kernel implementation when using XDP is also faster, so it was compared to kernel without XDP. Kernel with XDP, I think we are 30% faster or so if you have a kernel that can do XDP between different NICs, because most NICs can just send back out different topics. But yeah.
Next question again from the internet.
So R is asking, have you considered writing user space drivers for the more inherently insecure due to specification complexity things like the Bluetooth stack or things like this?
Yeah, would be interesting. Yeah, I guess that's a good topic for the research. We just went for a network because it's really common to have user space network stuff all directional. Like look at your iPhone or whatever, there's a user space TCP stack running on it. So yeah.
Number 3, please.
Hello, thanks for the talk. Just a little question. Does the IO MMU affect performance?
We are not yet sure. You can ask him afterwards. As far as we have evaluated it, it does not yet affect performance. There's also a paper called PCIe bench. PCIe bench something. Sitcom last year, I think, and you can read this paper. They have a performance evaluation of the IOMU. So yes, there is some effect because the TB size is smaller on the IOMU, but we couldn't measure it in our setup yet.
Microphone number 1, please.
When you access ring buffers, you usually have to have like an access once macro that you use to access the memory in C, because C is actually allowed to change the semantics of the implementation in a way where instead of, say, reading memory and storing in a variable, and then using that variable, would translate into something that would read the memory twice. And this was a problem with XSA 155, I believe, where in netback and netfront, the communication actually broke in that way because you had to talk to bug. How would you enforce like a single memory access in all of those programming languages?
Enforce is always a hard word. The thing is, most of these programming languages do need to copy the descriptor when using it. So the ring stores the descriptors. The descriptors are then pointers to some other buffer, and the critical part is when reading the descriptor. And I think all of the language implementation copy the whole descriptor, which is 16 bytes.
Okay, so the memory is always copied, guaranteed.
I hope so.
Please do check.
In the Go code, we had the atomic read thing, and I hope that only does one access, and otherwise it's considered a bug in Go if my atomic read twice. And C, I also copy it, I think.
We have time for one last question from microphone number 2, please.
How can we convince other people, especially other developers and the business people, of the necessity of moving away from C, learning a new language, and investing time of developing stuff in it?
What business people care about
C? I
C?
don't know. It's like a mystery to me why people keep writing stuff in C. Yeah. No idea, sorry.
Thank you very much to Paul, Simon, and Sebastian.
Okay, that's it for this advertisement stream. Awesome, we have one dislike. So we had somebody looking by, but